Hey Mark, why don't you take a break from that lead-based paint? Let's do some math.
Whoa, okay.
Have you ever wondered what powered your house?
I sure have.
Well, what if I said we could power all of Bloomington Normal using alternative energy?
I'd say that's pretty cool. Let's
go!
On the road again. Just can't wait to get on the road again. My love is making music with my friend. I can't wait to get home.
Windmills use the wind to spin a turbine, produce energy. Whoa! Look at it go!
On the road again. Going places that I've never been. Seeing things that I may never see again. I can't wait to get on the road again.
Now let's do some math. Hola! To find our annual energy output, or AEO, we have the equation AEO is equal to 0.01328 d squared v cubed, where d is equal to the rotor diameter and v is equal to the annual average wind speed in miles per hour. We then will plug in the values for our two variables. The rotor diameter of a Vista's V82 wind turbine is, d is equal to 269.028 feet, and the average wind speed, annual wind speed for Bloomington, Illinois is 7.4 miles per hour. Once we plug the values in for D and V, we get our annual energy output to be 389,482.725 kilowatts. Bam. From our previous equation, we were able to find the value that one windmill produces this many kilowatts, and then from physics.uic.edu, we were able to find that the average home in America uses 6,000 kilowatts per year, and then we plug in the variables y equal to the number of windmills, or x equal to the number of windmills, y equal to the number of houses in Bloomington Normal, and set it equal to 0 because we want the energy to equal out, and then we solve for x and we get the equation 6,000y over 389,482.725 is equal to x. With our equation, and based on information from the census of Bloomington Normal, we were able to find that there are 41,781 houses in Bloomington Normal. We plug this number into our equation and divide by the total voltage produced by one windmill, and it should give us, if we plug it in, 644. That is the number of windmills needed to provide electricity for Bloomington Normal. We now want to figure out the cost efficiency for each windmill. To install, and the materials for one windmill according to Vestas.com is $7,317,073.17. We plug this equation in to find our total cost times x, the number of windmills for Bloomington Normal. When we plug in 644, we get the total cost to be $4,712,195,122.
This sure is a bunch of scratch.
On the road again, like a band of gypsies, we go down the highway.
climb that.
What is that?
That's a solar panel that collects the sun's sunlight and converts it into electrical energy.
Could we use that to power Bloomington Normal?
Right, you are. Now let's do some math.
We're now going to find the cost of powering Bloomington Normal with solar panels. You see here, X is the kilowatts needed for the house, for one house. Y is the kilowatts needed for the panel. And we got this equation from shinesolar.net, I mean. And it's X over the hours sunlight in 1 year times 465.25 equals 9. And on weather.com said 56% sunlight a day on average is Bloomington Normal. So we take 24 hours times 0.56 times 365 days in a year equals 4,905.6 hours per year of sunlight. Now that we found the hours of sunlight in a year in Bloomington Normal, we're going to find X, which is the kilowatts needed for a house, for all the houses in Bloomington Normal. And it is 6,000 kilowatts times the amount of houses in Bloomington Normal. And we found this number from physics.usc.edu. And this number of houses is 41,781. That's from the Bloomington Normal census. And once we multiply those together, we get 250,686,000 kilowatts. Now that we found X, we also have the amount of sunlight hours per year. We divide this, and then we multiply times this number to find Y. This is Y. And since this is in kilowatt hours, we need it just in watts because solar panels are in watts, not kilowatts. So we need a factor label and put 1,000 watts times that, and that equals this number down here. And that's how much watts we need. Once we found how much wattage we needed to power Bloomington Normal, we had to figure out how many panels we actually needed. And we had the 285 watt panels, and we divided by that. And this is how many panels we had. And that's the best price to watt ratio we had. And that was from solarpanelonline.net. And once we round it up, because we can't have a decimal number, once we round it up and times it times 433, which is the average price of that certain panel, we got this number right here. Wow!
Whoa!
Look at how neat they are.
Whoa! Whoa, you look really interested in this guy.
These are pretty cool.
Did you know that if we take how many rotations he has in 60 seconds, we're able to calculate the kinetic energy he produces? Whoa! What do you think of that guy powering Bloomington Normal?
Well, jeepers, that sure would be swell. Look at that little guy go.
Now let's do some math.
Now we will see how many mice it will take to power Bloomington Normal for 1 year. To do this, we have to find the kinetic energy each mouse makes while spinning on a wheel. So that's 1/2 the mass in kilograms times the velocity, which is in meters per second squared. The mass of the mouse and the wheel in kilograms was 0.1935 kilograms, which we found from scaling the mouse. Next, we need to find velocity. To do that, we timed the mouse for 60 seconds and found on average for 1 minute it had 50 rotations. We also had to measure the circumference of the wheel, which was 0.35 meters. If we take our rotations per minute over 60 seconds, we find that the mouse makes 0.833 repeating rotations per second. Now that we have the rotations per second and the circumference of the wheel, we can find out what the velocity of the mouse is. So we take 0.352 meters times 0.833 rotations per second to find the velocity to be 0.2933 repeating meters per second. So now that we have the mass of the mouse and the wheel and the velocity of the mouse, we can put that into the equation to find its kinetic energy. So 1/2 times the mass times the velocity squared gives us that 0.00393000799 joules is what the mouse creates in 1 second. Now we take the number of joules, we have to convert it into kilowatt hours because that's the units we're using for the housing. To do that, we multiply the number of joules times 0.2 2.77 times 10 to the negative 7 kilowatt hours, which gives us 1.029 times 10 to the negative 9th kilowatt hours, which is how many kilowatt hours a mouse produces. EnvironmentalGraffiti.com gave us that a mouse spends 11 hours awake every day, so we multiplied that by 1/3 to find 3.66 hours, and this is the predicted value the mouse will spend on the wheel. 3.66 hours times 365 days gives us the amount of time spent on the wheel in a year in hours, which is 1,338.445 hours. Next, we multiply that by 60 minutes, because there's 60 minutes an hour, and we predicted the amount of energy generated for 1 minute, so we have to have the amount of time spent on a treadmill in 1 minute, which was 8,307.3 minutes. We take that value times the amount of energy generated per minute from the mouse to reach a value of 8.76955,716 times 10 to the negative 5th kilowatt hours per year, which is the generated energy for one mouse on a wheel. So now we will solve for the number of mice needed to power Bloomington Normal for 1 year. We take the amount of energy one mouse generates in 1 year minus the amount of energy Bloomington Normal needs, which we've used and obtained from the previous equations for windmills and solar panels. We solve for x by subtracting the 250,886,000 kilowatt hours needed for Bloomington to the zero side of the equation, and then we divide by the number of kilowatt hours a mouse generates in a year, and solve for x. We found that the number of mice needed to power Bloomington for 1 year is 2.86 times 10 to the 12th mice. So now we have the number of mice needed to power Bloomington for 1 year times the price for a mouse for 1 year. This includes food, bedding, and the actual mouse, which was obtained from PetSmart.com. So by multiplying the number of mice needed times the price of each mouse, we found that to power Bloomington Normal for 1 year solely on mice running on a wheel, it would be 1.93908 times 10 to the 14th dollars.
That's more than my allowance.
Now that we've done all our calculations, we can compare the prices for the mice, the solar panels, and the windmills. As you can see, it's clear that the windmills would be significantly more cost efficient than the mice and the solar panels, and therefore windmills would be the best bet to power Bloomington Normal.
Mr. Deering?
Yes.
How do you feel about alternative energy?
It's got its place. I guess there's good alternative energies and ones that aren't so efficient. So there's a lot of them out there.
Okay, and which do you think is the most efficient and why?
Efficient is probably going to be hydroelectric or geotidal are two really efficient. And solar is solar photovoltaic. Solar would be pretty efficient. The others, like wind turbines, have found to not be as efficient, even though that's kind of what we got around here.
Okay. And do you think that a town like Bloomington Normal could run solely on alternative energy, such as windmills or solar panels or hamsters?
Hamsters? I don't know about hamsters. It could. It would just take a lot of them, and then you get the efficiency issue, that whole thing. But it could, definitely. Just need a lot of them.
Okay, thank you.
You're welcome.